Okay, now we finished the two examples of the spring mass system. The next two examples I'm going to talk will look very different from the outside, the net shell. But I want you to pay attention to see underlying math, how close they are. Again, now what I have is here a floating form, whatever object here in the water. If you push a little bit down, you understand that the motion of this floating form, let's assume it's lighter than water, they're going to bounce back and forth, right? But how do you get the exact motion? This is the next study. For the oscillation of the float, we start from a rectangular box, then we talk about a sphere, and as an application, I would love you to think about my AUV, which is more or less like an olive shape, and it's ellipsoid. And if I push it, how is it going to bounce in? Because the resistance of the water as the force floating up and the weight pushing down, you see there's a balance. So in this case, what kind of force you have? You have the buoyant force. W stands for the weight. F, what's the F? Could be the water resistance, friction. Okay, you have three forces. So WF goes down this way, the buoyancy goes up. And then we can select the equilibrium point as z equals 0. And then we put the little point on the top, talk about the derivative to time, put the 2 points on the top, is the same as take a 2 prime here, just the shorthand for derivative to time. So by Newton's law, the second derivative times mass equal the total force, which is 3 here. And then you get this equation. That's the inertia, the resistance of the water, and that's the buoyant force and the weight. So it looks very, very similar to what you have in, let me see here. Here, see, second derivative, resistance, and this one probably a little bit different, and then you have an FT. So looks similar, but the only thing really different is this. The buoyant force equal the total volume of water this object expelled out. So the volume this object sinking down is what matters here. The total weight. You see this rho g is the density. The density times the volume equal the total weight of water. So the buoyancy really equal the total weight of the water occupied by this sinking submerged component and the part below the surface of water. So you understand this, we divide by n, you got this second derivative of the motion, and then this is the resistance, there's a pointer here, I hope you can see the pointer here, and then that's the buoyancy, that's the weight, but we divided m. So in short, The only difference, the only thing you really need to care is the volume here. You know, the more you submerge down, the bigger the volume is. That's very clear. So in order to make it easier, the things is always start from property box. In this case, if you have a box and assume the box does not wobble, it's go still balanced down and up, you maybe get some wall on the side to hold it. So if that's the case, you know the volume equals the surface area, which is, let's say it's a square, that's L, and that's the surface area here. Then it's the L square times the Z, which is the depth submerged. So the volume is really simple. And then, of course, you need to times the density. That will be the buoyance. If this is the buoyance, you see, by Newton's law, the inertia equals, this is equal. Buoyance minus the weight, And there's another term, maybe. How about, let's again start very simple. We make this B equal 0, no resistance. That's how we make things easy in the first time. If that's the case, what you have is 3 terms. And if you have these 3 terms, I can play a little trick again, just like the spring, by shifting the origin. By shifting the origin, I mean I will let this sink down a little further, and this little further sinking down will counterbalance the weight of this object. Then I choose the Z equals 0, not the surface of the water. Instead, is the Z equals 0 here, which balances the weight, and then I don't need to consider the weight. If I don't need to consider the weight, all I need is the Z, which is further sinking down from this 0 times the surface area, that's the volume, and that's the only buoyance you need to think. And then what you get is this equation. Doesn't matter how hard it looks like, it's really the second derivative equals some kind of constant times Z. That we know. That's just the spring mass system. This one looks complicated, but nothing more different than we have here. That's it. The same as this, if I use the same constant. So what we discovered is, if we make the situation perfect, not consider the resistance and your motion, it's like a perfect harmonic motion. It's like the spring mass system oscillating forever. That's of course not true. But that's how we started the things to make it easy. In the second situation, I made it a little harder. Assume the B is not 0. And then we make this B as the resistance equals 3 pounds per second per feet. Let me see, that's the B, okay. If that's the case, we just need to add this term. And again, this is double derivative, that's a derivative, that's itself. And again, by choosing the right equilibrium point, you can get the homogeneous. In other words, you can always cancel out the weight by choosing the slightly different equilibrium point. You balance the weight in the first place. So that system, if you look at it carefully, it's just the double derivative plus one constant, single derivative, another constant, this, and it itself. That equation is the same as this one. You see it? Just the B and the K. And the same as this one. Can you see it? If I put the 2 and the 32, same equation. So what I'm saying is, you look at a very different problem, you find exactly the same type of equation in the mathematics level. We can also give you like a circuits with the resistance, inductance, and the capacitor. You can get the same equation if you learn differential equation. Okay, once we get all those, we put into number. And again, I like to make things simple because this is for theory. Let m equal 1, the b equals 3, and forget what I put this VL, maybe the L is just equal 1. That's how I do. Anyway, this is the system we have. And the solution, I can use Stellar to solve it again, right? But this time I did not use Stellar. Instead, I used Maple to solve it. And this curve is really like that. And you can see it here. They use the so-called Runge-Kutta subroutine, and this is kind of oscillation. As you expected, the amplitude got smaller and smaller, and we call this as attenuating oscillation. Basically, because the water, of course, is not like air, has a big resistance, and dissipating the energy you give in the beginning. So the third example, when we think about a floating box, turned out it's the same mathematics equation model as the spring mass system. Let's go to the last example.